Alright, hello class. In this video we are going to just look at more examples of the chain rule, and we'll round it off with more verification of why the chain rule works, a little proof of it. I meant to say in the last video, you're probably at a point where you can get rolling on the homework, at least get started. We're going to be looking at way more complicated examples in this particular video, just so you can see some of those. And all right, let's just get to it. All right, so for this particular example, y equals cosine to the 7/4 of 4x cubed. Again, my advice for these, if you're having trouble with them, is always move that power to the outside, because this is cosine of 4x cubed all raised to the 7/4. Okay, that's what that cosine of the 7/4 means. So when you go to try and do the derivative, you're going to ignore the inside, bring the 7/4 down. Right, so this will be 7/4 of the stuff left alone. So I'm not even worried about what is on the inside here. Just copying it down, and then it'll be the 7/4 minus 1, which will be 4/4. Okay, so it's going to be this thing to the 3/4. Okay, then we multiply by the derivative of the inside. So this is the inside, and the derivative of the inside goes here. Well, the derivative of the inside is cosine of stuff. So the derivative of cosine of stuff is negative sine of that stuff times the derivative of that stuff. So here's the stuff, derivative of the stuff. Well, the stuff is 4x cubed, so it will be 12x squared. Right, and then if I try to go in one more time, so the derivative of 4 something cubed will be 12 something squared times the derivative of that something, or the derivative of x is 1. So that's when you know you're done going, when that last piece, okay, it ends up being having a derivative of 1. Now, if you have trouble following that, of course, we can always do a chain, like, and again, that's why it's called the chain rule. We can do a chain where if we rewrite what we had here, okay, we can write it as a chain of different letters. So we could say that this stuff here is u, right? So we end up with u to the 7/4, where u is cosine of 4x cubed. Okay, and so what's on the inside of cosine we could call v. So we could say that u is just cosine of v, and then v is 4x cubed. Okay, so then when y is u to the 7/4, okay, its derivative, y prime, will be 7/4 u to the 3/4 times u prime. Okay, well, u prime, if u is cosine v, u prime is going to be negative sine v times v prime. Okay, so if we put that in, right, negative sine v times v prime, perfect, and then v prime, well, v is 4x cubed, then v prime is 12x squared. So if we put that in here for v prime, and then replace anything else that we have, right? The 7/4, our u was this cosine of 4x cubed. Okay, and v was 4x cubed. So this will be negative sine of 4x cubed, and then we'll have the 12x squared. All right, so you just plug everything back in, and now we can go about simplifying if we like, or we can just leave it like this. I would probably simplify this one at least by bringing the 12x squared and the negative out front. So the 12 cancels with the 4 and leaves a 3. So we should get negative 21x squared cosine of 4x cubed. Oh, sorry, this should be raised to the 3/4. Forgot that. Sorry, a little typo there. Oops, cosine of 4x cubed all to the 3/4 times sine of 4x cubed. All right, and there we go. There's our final answer. However you decide to do it, whether you do it just brute force your way through it, as each time you need to take a derivative, you just take a derivative, or if you need to set up a chain of letters, U, V, W, what have you. However you decide to do it, you should eventually, if you're careful, get to the correct answer. All right, next up, let's look at sine to the 5th of cosine of 3x. So remember, whenever you see something like this, this is sine of cosine of 3x, all raised to the 5th. All right, so we'll bring the 5 down. So essentially, this is stuff to the 5th. So its derivative, y prime, will be 5 times the stuff left alone raised to the 4th. Then we start worrying about the derivative of the stuff. So this is the stuff, or actually let me call it the inside. So this is the inside. So we want to put the derivative of the inside. But the inside is sine of some stuff. Okay, so its derivative is going to be cosine of that stuff, right, times the derivative of the stuff. Okay, so cosine of the stuff left alone, well, that stuff is cosine of 3x, then times the derivative of that stuff. Well, the derivative of cosine of 3x is going to be negative sine of 3x times 3. Okay, so when it's all said and done, when we simplify this, let me clean this up a little bit. It's all said and done, I'm going to bring the 3 and the negative outside, so we'll get negative 15 sine of cosine of 3x all to the 4th times cosine of 3x times sine of 3x. Okay, so this is just a straightforward way to do it, one after the other, and you just differentiate as you go. Let me show the chain way, because I think when you're first learning, I find students tend to appreciate the chain way a little bit better. So let's write it like this: sine of cosine of 3x to the 5th, and let's say that this whole thing on the inside is u. Right? So this will be u to the 5th, where u is sine of cosine of 3x. Okay, well, I'm going to call what's inside of sine v. Right, so v is going to be cosine of 3x. Okay, and so u is sine of v. Okay, and v is cosine of 3x. And we could probably just say v prime, since it's just a single thing here, that will be negative sine of 3x times 3, since the derivative of 3x is 3. So it's negative 3 sine of 3x is v prime. Okay, so y is u to the 5th. So y prime is going to be 5, u left alone, okay, to the 4th, okay, times u prime. Okay, well, u is sine of v, so u prime is going to be cosine of v times v prime. Okay, so in this next line here, I'll write this as 5 u to the 4th and then u prime I'll replace with cosine of v times v prime. Okay, well now we already found v prime. It's this, negative 3 sine of 3x. So we'll put that in to our v prime. All right, so we'll get 5u to the 4th times cosine v times, and be careful here, negative 3 sine of 3x. And now we can just start plugging, backfilling, because we're to the x's now. So v, we can put v into here, okay, and then we can put our u into here. Okay, so when it's all said and done, our y prime is 5 all times sine of cosine of 3x to the 4th. Cosine of v, well, v was cosine of 3x. Make sure I have enough parentheses here. And then we just rewrite this, negative 3 sine of 3x. So as you see, doing it this way, we still get to the same answer we did before, possibly in an easier fashion since we're reducing it down to something easier to deal with each time. All right, here's a sort of a famous problem, or a version of it that I see countless times, which is y equals the square root of x plus the square root of x plus the square root of x. All right, so we have the square root of stuff eventually, so essentially. So if I let this on the inside be u, we basically have the square root of u, where u is that junk on the inside, which is the x plus the square root of x plus the square root of x. Okay, well, I'm going to now take this funky stuff on the inside and call that v. So our u is just x plus the square root of v, okay, where v is x plus the square root of x. Okay, now I should be able to do our sort of chained reasoning here, I guess is what you could call it, because we have y is equal to the square root of u. So y prime is going to be 1 over 2 root u times u prime, or a little simpler, y prime is going to be u prime over 2 root u. Okay, well, u prime, if we do it here, let me do it right here, u prime, well, the derivative of x is 1, and the derivative of the square root of v is v prime over 2 root v. And this actually, now that I think about it, may get a little complicated if I try to do it in one fraction, so I'm just going to put u prime right here. Okay. I'll do the same thing here. I'll say 1 times v prime. Okay, so now that I have this u prime, I can replace it with what we have here. Actually, maybe I should do that on a new line. Okay, so same thing here. I'm just now replacing the u prime with a 1 plus 1 over 2 root v, then times v prime in here. So we have to keep that 1 plus, okay? That's important. Oops, and that's a really common mistake I just did there, so don't do that, okay? And now v prime we can calculate. V prime will be 1 plus 1 over 2 root x. So we can plug that in right there. Okay, so the v prime gets replaced with a 1 plus 1 over 2 root x. Okay, and I did it again. That should be a v. Okay, and so now we can plug in the other things. We can plug in the u, that original u, and basically get back to our x's. Okay, so y prime is going to be 1 over 2 square root u. Square root u is this large thing. So actually, I'll just do it like this. That was x plus the square root of x plus the square root of x, I believe. Okay. Then it will be 1 plus 1 over 2 root v, and v was x plus square root of x. Okay, times 1 plus 1 over 2 root x. Okay, very nasty. Okay, I will not argue with that. This is disgusting. However, thanks to basically chaining our u's and v's, it looks nasty, but it wasn't as bad as trying to do this, say, step by step. All right, next up, let's say we have e to the x squared plus 1 times sine of x cubed. Something to note here is this is a product rule with chain rules inside. Right, because we have two things multiplied together. Okay, so when we go through this, we need to employ the product rule, but each one of these is also going to have a chain rule. So it's going to be the derivative of the first. So the derivative of the first is e to the stuff, okay, times the derivative of the stuff. So e to the x squared plus 1 times 2x. Then times the second function left alone, plus the first function left alone, times the derivative of the second function. So the derivative of sine of stuff is cosine of that stuff times the derivative of the stuff. So the derivative of x cubed is 3x squared. Okay, so I'm going to rewrite this in an easier to read way as 2x e to the x squared plus 1 times sine of x cubed. And on this side, I'm going to bring that 3x squared outside. So 3x squared e to the x squared plus 1 times cosine of x cubed. Okay, we could simplify this a little more by factoring or whatnot, but I consider this good enough. All right, so notice how, yes, I did a product rule on the outside, but every time I needed to take a derivative, it was a chain rule. All right, next up, let's say we have the tangent of x to the 5th times e to the 7x. So this is actually the opposite. This is a chain rule with a product rule inside. Okay, so in other words, this is tan of some stuff. Right, we can think of this as tan u, where u is x to the 5th times e to the 7x. So when we go to find u prime, that's going to be a product rule. Okay, so y prime is going to be secant squared of the stuff, which is x to the 5th times e to the 7x, times the derivative of the stuff, which is going to be a product rule. So 5x to the fourth times the second function left alone plus the first function left alone times the derivative of the second function, which will be 7e to the 7x. And I would just leave it like that, honestly. All right, here's another example of the other option. This is a product rule on the outside because I have some function times another function. All right, we could think of this as an f times a g. But then those f's and g's are chain rules. So this is a product rule with chain rules inside. Okay, so when we go to calculate y prime, it will be the derivative of the first function. The derivative of the first function, e to the stuff, well, that's always itself. Okay, times the derivative of the stuff. Well, the derivative of the stuff is going to be 2x plus 2 in this case. Okay, now times the second function left alone. Okay. So here is the derivative of, if I call this f and g, f prime, and this of course is g left alone, then it will be plus the first function left alone, so we'll just copy that down, then times the derivative of the second function, and this is stuff to a power, right? So I'm going to bring the 5 down. It'll be 2x minus 7 all raised to the fourth, but we need to multiply by the derivative of the inside, which in this case is just 2. Okay, so here's f left alone and the derivative of g. Okay, so to make it a little more readable, this would be 2x plus 2 times e to the x squared plus 2x plus 5 times 2 to the 7, or 2x minus 7 all to the fifth plus e to the x squared plus 2x plus 5 all times 10 times 2x minus 7 raised to the fourth. Okay, and honestly, I would just leave it like that. You could factor, you can factor a lot of stuff out, and you know, whatever. We can just leave it like this for now. All right, now this, I just want to talk about some notation messes that the book pulls. I understand why people have trouble with this. The difference between sine squared x versus sine x squared. Something to always keep in mind is that exponents only affect what they touch. Because remember, with the order of operations, exponents go before other things. So that's the difference between, say, negative 5 squared and negative 5 all squared, right? Remember, order of operations, you do the exponent before you do, say, multiplication. So in this case, what is the exponent touching? It's touching the 5. So this is negative 1 times 5 squared. You would do, by order of operations, the 5 squared first. So this would be negative 1 times 5 squared, which would be 25. So this comes out to be negative 25. However, in this case, you do the exponent first. So this would be negative 5 times negative 5, which would be positive 25, right? That's the difference in these two things. The exponent is only going to affect what it is touching. So in this case, it is touching the sine, right? So this is sine of x, or sine x all squared. Okay, and so this is just the notation we use for that. Whereas here, the exponent is touching the x, so this is sine of x squared. Okay, it's messy, I know. So if this were f and this were g, f prime would be 2 sine of x times cosine x. Okay, either using the chain rule or the product rule. On the other hand, g prime would be cosine of x squared times 2x. Very different things, even though they're very easy to confuse. Okay, but just remember, exponents only affect what they touch. If they touch a parentheses, they affect everything in the parentheses. If they don't, they only affect the number or variable or function or whatever it is they are actually touching. Okay, so hopefully that helps with some of these weird notation things you might run into. Okay, I want to take another look at absolute values. We already looked at this earlier in this module, right? So the absolute value of x, it's x when x is greater than or equal to 0, or it's negative x when x is strictly negative. If we remember, it made this V shape for the graph. Right, and we found that it was not differentiable here. And that's mainly because let's say if we call this f of x. Okay, on this side of 0, f prime of x is going to be 1, and on this side of 0, f prime of x is going to be negative 1. Right? Because you could think of it as, well, if you think of it as the slope of the tangent line, or however you want to think about it in terms of derivatives, we discussed that earlier. So the derivative function ended up being, so 1 on the positive side, negative 1 on the negative side, and it would have a hole here if we were looking at f prime. Right, so this is, and that's because the limit just doesn't exist, so the function itself does not exist. Okay, I want to look at another way we can define the absolute value, and we've talked about it briefly, not as a definition, but just as the way things work algebraically. Okay, and that's simply as the square root of x squared. You can define the absolute value as this way, the square root of x squared, because we've talked about it before. If you give this, say, a negative 5, you're going to have the square root of negative 5 all squared, which will be the square root of 25, which is 5. And if you, that shouldn't be parentheses there. And if you give it a positive 5, of course, it's just going to take the square root of 5 squared, which is, once again, the square root of 25, which is 5. Okay, so this acts exactly like the square root of x squared. So when we just cancel this as x, we're actually doing ourselves a disservice because it has to be a positive x, or the absolute value of x. Okay, so why am I talking about this? Well, through this definition, we can actually look at the derivative of the absolute value of x. And we've looked at it graphically, and we know it should be negative 1 on the negative side and positive 1 on the positive side. But we can further verify this because the derivative with respect to x of the absolute value of x, well, that's going to be the derivative with respect to x, the square root of x squared. And this we can use the chain rule because this is the square root of stuff, right? So it should be the derivative of the stuff, which is 2x, all over 2 times the square root of the stuff. Right, so here we use the chain rule. Okay, so the 2's cancel, and we get x over the square root of x squared, which is the absolute value of x. Okay, so it turns out that the derivative with respect to x of the absolute value of x is x over the absolute value of x, which, well, turns out when x is positive, you get x over x, which is 1 when x is strictly positive, and then you'll get x over negative x, which is negative 1 when x is negative. And this will be undefined when x is 0 because you'll get 0 over 0. Okay, well, check it out. That's exactly what we had determined before, just looking at the tangent lines and other stuff like that. So, yeah, the derivative of the absolute value of x is x over the absolute value of x. Now, why is this helpful? Well, because now, if I want to find, let's say, the derivative with respect to x of sine of the absolute value of x, well, that's just going to be cosine of the absolute value of x times x over the absolute value of x. Okay, so we can actually start incorporating absolute value functions into our derivatives. So like for the derivative with respect to x of the absolute value of x cubed, that will be 3 times the absolute value of x squared times x over the absolute value of x. Oh, well, this is interesting. All right, because here the absolute value, well, some of the absolute values cancel, and so we get 3 absolute value of x. Okay, very, oh yeah, and times x. So 3 absolute value of x times x. Okay, if we look at the graph, this is the graph of the absolute value of x cubed, and then this is the graph of 3 absolute value of x times x. Okay, so it does definitely seem to line up, because as this function decreases, the derivative function is negative, and as it increases, it's positive. Okay, so it's just an odd result. Okay, so if we look again at this particular result, the sine of the absolute value of x, here's sine of the absolute value of x. So notice it basically just looks like sine, except on the negative side it's been flipped over. So we definitely have a place where the function is non-differentiable, right? There's a cusp there, which we see there. If we try to plug 0 into the derivative, we get undefined. Okay, now if I graph that derivative formula, we see this in orange. So what's happened is, yeah, it's essentially positive cosine on this side. Okay, so let me show you just normal cosine. Right, here's normal cosine. And then on the negative side, it's negative cosine. Okay, so here in the purple. So on the right side, what we're basically getting is regular cosine, and on the other side, the negative cosine. Okay, so, but also where this spike is, we have a jump, and that jump is represented by this. Since this is also often called the signum function or the sine function, it is adding a jump into this cosine function here. All right, this can also lead us to this, so the other way around, where if we have the derivative with respect to x of the absolute value of u, we'll get u over the absolute value of u times u prime. And this is still a sine type function. The u over absolute value of u is basically going to give us 1 whenever u is greater than 0. So whenever u is positive, it's going to give us a positive 1, and a negative 1 whenever u is negative, and of course it will be undefined whenever u is 0. Okay, so that means we can have multiple places where we'll have those sort of jumps. So for example, if we wanted to find the derivative with respect to x of, let's say, the absolute value of x cubed minus x squared minus 6x, okay, we're going to get, well, it's the u, x cubed minus x squared minus 6x, all over the absolute value of u, x cubed minus x squared minus 6x. Okay, and then we'll multiply by the derivative, which will be 3x squared minus 2x minus 6. Okay, so to show what's going on graphically here, okay, so this is just the function in red here of x cubed minus x squared minus 6x. So this is what happens without the absolute value. Okay, but when we add in the absolute value, okay, all the places where the function is negative are going to flip up to be positive. So this is the graph that we get. Okay, so we'll have a non-differentiable point here, here, and here. So there are 3 places where this function will have no derivative, and we will likely see jumps or other weirdness happening at these points when we graph the derivative. All right, I've zoomed out a little bit. And so when we graph the derivative, we see the jumps exactly where we have these spikes happening. Okay, and so what's essentially happening here is these are all pieces of the original derivative function for the function without the absolute value. So that's what is here in orange. And as you can see, places where in certain places we get the exact same function, but in others we are flipping it around the negative, and that's where that sine function, the absolute value divided by the original, comes from. Okay, so it's basically pieces from that function, but anywhere there is a spike that's causing a jump. Okay, anyway, I thought that was interesting, something to look at. We will be seeing that absolute value thing show up a little bit more in the future. All right, and so because of that, I thought it would be a good idea to take a look at it while we're playing with the chain rule. Okay, so for the last bit of this lecture, and really this is more for people who are interested, more so than it being required, but a natural question here is, can we get to the chain rule using the limit definition? Okay, and the answer is, of course, yes. All right, so what we're going to consider is the function f of g of x. All right, we're going to consider the composition function. All right, so we're going to let f and g be all functions and nice and differentiable and blah, blah, blah. Okay, but what we want to look at is that the derivative with respect to x of f of g of a, so we're going to use this particular version of the limit definition. It's going to be the limit as x goes to a of f of g of x minus f of g of a all over x minus a. Okay? And what we end up doing here is multiplying by g of x minus g of a all over g of x minus g of a. Okay? So, if I sort of swap these denominators around, we get this is the limit as x goes to a, okay, of f of g of x minus f of g of a all over g of x minus g of a times g of x minus g of a all over x minus a. So all I've really done is swapped these two denominators here, which we can do since we're multiplying these two fractions. Now, one thing to note is that as x goes to a, okay, g of x goes to g of a. And again, I didn't put a bunch of conditions here. We're assuming that everything's differentiable and nice and what have you. Okay. All right, so what we can actually consider here is rewriting this limit in terms of this. So we could say that this is the limit as g of x goes to g of a of f of g of x, right, minus f of g of a all over g of x minus g of a, okay, times the limit as x goes to a of g of x minus g of a all over x minus a. Well, this is going to be g prime of a. Okay, now this, all we've done is rewritten, okay, how the limit works. Right, so it's almost like if we let say y or u or what have you, so go to g of a, which we could call v. So let v be g of a and u be g of x. What this ends up giving us is this is the limit as u goes to v of f of u minus f of v all over u minus v times the limit as x goes to a of g of x minus g of a all over x minus a. Okay, so this is actually the definition of f prime of u. Sorry, of v, my bad. F prime of v. Okay, and this is g prime of a. Okay, then if I replace the v with the g of a, we finally get down to f prime of g of a times g prime of a. Okay, which, what did we start with? We were looking at the derivative of f of g of a. We got its f prime of g of a times g prime of a. All right, now this is a bit hand-wavy. There's some stuff we're missing here. I don't want to get into the weeds with a full-blown proof of this, but this is the general idea of how we get the chain rule using the limit definition. And so that's our answer. Essentially, it's yes. There's some tricky things we need to worry about, but for the moment, this is good enough to, hopefully, at least convince us that we can get there, plus or minus some technicalities that we would need to worry about. But other than that, that is pretty much the chain rule. So as I mentioned in the first video, this is where calculus starts to get really complex. I feel like students get this wrong impression early on because the basic limits aren't too bad for most people. Basic derivatives aren't too bad for most people. But once we hit the chain rule, that's when we really start seeing the complexities emerge from calculus. All right, so that'll do it for that. So I will catch you all on the next one. Cheers.